Welcome back to the afternoon session. You may already know, but we are discovering new cases of COVID among the participants every day. So on behalf of Simons, I strongly encourage everyone to wear masks, especially if been exposed, in close proximity of people who have tested positive. I have masks here for anyone who. Just as a gesture of solidarity. Okay, thank you. Let me know if you want one. Yes, of course.
And also get tested if you need to collect tests.
Single tests?
People in room 118, yeah.
That's right. You can
Yeah,
get one.
they have tests available, but you have to tell them you are a speaker or something like that. Yeah. No? Oh.
Okay, and now it's my pleasure to have Suraj, who graduated from Stanford a few years ago and now is an assistant professor of economics at Cornell, to talk about learning through the grapevine.
Thanks, Amin. So thanks everyone for joining today, and special thanks to the organizers for inviting me to this very nice conference and bringing together such an eclectic group of researchers. It's been a lot of fun. Today, I'm going to present joint work with Matt Jackson and David McAdams. And the title of this paper is Learning Through the Grapevine, the Impact of Noise and the Breadth and Depth of Social Networks. This is a paper that tries to think about misinformation and some simple tools that we might use to combat it. And to frame our main question, I'm going to show you a couple of quotes. So here's a quote by Senator Elizabeth Warren. She says, "The safety of our democracy is more important than shareholder dividends and CEO salaries. And we need tech companies to behave accordingly. That's why I'm calling on them to take real steps right now to fight disinformation." Okay. However, Mark Zuckerberg disagrees with this point and says, "I don't think that Facebook or internet platforms in general should be arbiters of truth." This exchange sort of highlights one of the main tensions that arises when we think about using traditional tools like censorship and fact-checking to combat misinformation. And that tension is that at the end of the day, we have to appoint somebody to be an arbiter of truth, someone who's going to do the censoring and fact-checking for us. And there's no easy answers as to who's the right person for the job. So on the one hand, we might worry about giving governments this power. We might worry that they encroach on our freedom of speech or use this power towards various political ends. On the other hand, we can't rely really on platforms to properly regulate themselves. They might have incentives to appear as neutral channels so as not to alienate certain groups of users who might perceive them as being biased. Similarly, these issues of bias also come up to some extent when you rely on things like crowdsourced fact-checking. Now, even if you were to go ahead and do censorship and fact-checking, there are other limitations. So first of all, there's a huge volume of communication online. You can't hope to cover all of it or even a majority of it. You might rely on various algorithms to help you do this, but algorithms have trouble with things like satire and humor, so they might not be able to tell what's true and what was just a joke. And finally, there are some channels of communication which are meant to be private, and these are encrypted channels like WhatsApp or communication over other messaging platforms. Right? And so here we can't even observe the content that's being sent around, so we can't actually rely on these tools. So that's a limitation. So in light of all of these observations, we ask the following question in this paper, is how do we promote truth without actually taking a stance on what's true or what's false, and without actually even observing the content of the messages that are being sent out? So the plan in this talk is to do the following. First, I'll show you a very simple and stylized model of noisy communication on networks, and then a model of how nodes react to the information that they hear from their networks. And then we'll turn to looking at neutral policies that reduce misinformation without relying on the policymaker's prior about the true state, or without relying on the policymaker actually having to observe the messages that are being sent. All right, so let's start with a model of noisy communication. Before I get into the model, I'm going to show you just a few stories to kind of motivate the way we think about things. So Simmons, Adamic, and Adar in this 2011 paper give an interesting account of a series of tweets that were posted. So initially, someone writes, street-style shooting in Oxford Circus for ASOS and Diet Coke. Let me know if you're around. This quickly became retweeted with the additional message, shooting in progress in Oxford Circus, what? Which then got picked up by someone who wrote a lot more definitively, shooting in progress in Oxford Circus, stay safe, people, all within 3 minutes. Okay. So a series of what seemed to be misunderstandings led to the spread of some false information. Of course, sometimes misinformation can be spread more deliberately. So here's one such account. The Yellowstone Volcano Observatory wrote an article about the repairs that they did for a monitoring station that was damaged during some storm. Very quickly, a tabloid wrote an article about this, basically really exaggerating the truth, and claimed that Yellowstone was not monitored. And in fact, they did a really poor job of reading the contents of the original article. So some words like borehole became boreal, and so the messages really got mixed up. And it turned out that this misspelling of borehole persisted, and then the same misinformation that was written up in the tabloid persisted in future social media reports that picked up on that article. So here we have a mix of some deliberate mutations along with some random errors as well. The one question you might ask is, what's the frequency with which these kinds of things happen? Maybe one way of answering it is through introspection. You think how often do these types of miscommunication arise in your own day-to-day lives? There's also some evidence to suggest that in online communication, these numbers aren't small. So Epidemics et al. In 2016 have basically showed that a variety of viral memes had pretty high mutation rates and a lot of variance. So one meme was reposted 470,000 times with an 11% mutation rate, and it ended up having over 100,000 variants. Okay? And this wasn't uncommon in their data set. Now, this kind of thing need not happen only in online communication. Another piece of evidence is that there are over 500,000 textual variants of the Greek New Testament, not including spelling errors. So these are substantive changes to meanings of various passages. And so these kinds of errors in communication are pretty prevalent, it seems. So this is going to motivate us to try to write down a model that captures noisy transmission in a setting where messages are sequentially relayed. Okay, so this isn't a model of Twitter or anything like that, but to give a more concrete example, you might think of a messaging platform like WhatsApp, okay, and sort of private communication between individuals. Okay, so here's a model. I'm going to think about a state of the world omega, which is either 1 or 0. Okay, so you can think of this as encoding climate change is real or climate change isn't real. This diet will be helpful to lose weight, or it won't be helpful. You can also think about states that are messages that aren't too far apart. So I think about one message being this medication or vaccine has no side effects, and another message being that side effects are very, very rare. And there's a probability theta that the state of the world is 1. Agents hear IID binary signals about the state with some probability R, and they're initially uninformed with probability 1 minus R. Okay. And then noisily, messages are going to get relayed to the agent's neighbors in this network. And I'm going to tell you what noise looks like and what the network looks like. So there's a probability mu sub 0, 1 and a probability mu sub 1, 0, both less than 1/2 of messages mutating in transmission. Mu sub 0, 1 is the probability that a 0 message that I have gets mutated into a 1 message when I pass it to the next person. Mu sub 1, 0 is the probability that a 1 message gets mutated into a 0 message in transmission. And these mutations are going to be IID at each step of communication. And they can be, you can think of them as being random or deliberate. So one thing here is that the agents aren't strategic. Okay, so here, at the end of the day, people are making some choices. Those are going to result in certain probabilities of messages being right or wrong. That's not to say that incentives aren't important. I'm an economist, and so are my co-authors. So we will you'll never catch us saying that. It's just that here in these sort of settings, we don't really, there might be a variety of reasons why people are actually sending various messages. we want to focus on just sort of the n error probabilities that these things generate and the probabilities of transmission and work with that and see what we could say in this sort of model without incentives alone.
I'm sorry.
Yeah. So all I mean by that is there might be certain agents in the network who are more prone to saying one sort of message than the other. And so their location itself might be random in the network. And so in that sense, it can be captured by these probabilities.
You mean by so deliberate means that actually I just use the one is larger than my.
So we think of these from a sort of ex ante perspective at every step of communication. These are the probabilities of mutation failures. But there could be certain agents who are, for example, going to say that the message is 1 even if they hear a 0, and vice versa. And those kind of agents might occur in the network with some probability. And so we're capturing from an ex ante perspective, there are just certain probabilities that these kinds of mutations happen at every step of communication based on the identity of the individuals who are passing it and just the noise inherent in the transmission process.
So it doesn't matter whether you sort of flip a coin or which agents are actually malicious and which ones are not. And if you flip it while you do the same thing, then you just end up with the same one. That's what it is. So it could be random or delivered, just means these are two different
interpretations. This is just about interpretations. Yeah. Now, so this is one type of noise, the content of messages changing. Another type of noise is that there might be transmission failures. So I tell Amin something, but he doesn't think that it's important enough to relay to Kitse, and so he might drop the message. So there can be probabilities, P sub 1 of passing a message of type 1, and probability P sub 0 passing a message of type 0. And of course, in general, these P sub 1s and P sub 0s might be different. So you might be more likely to pass along a message if you're reporting, if you're telling a funnier joke, or you're reporting news, or saying something that has a sort of statistically significant result, or passing along a more salacious rumor. So the actual content of the message can, of course, affect its transmission probabilities. But in today's talk, I'm going to abstract away from that and just assume that there's some constant probability of messages being dropped at every second. Okay. So I still haven't told you what the network looks like. But before I get to that, let me describe what a chain of message passing is going to look like. And then I'll get to them. Okay, so there's some initial source who got some signal about the state of the world and is passing this along. And ultimately, there's some end receiver who I'll call the learner who observes some noise of version of this initial message. Okay. And the process, yeah, go. And so the process looks something like this. Suppose initially that the source observes a signal of type 1. This message survives and doesn't mutate with some probability, and so it's going to be transmitted as a 1 message. With some probability, it survives, but mutates and it gets transmitted as a 0 message. And with some probability, it's going to be dropped entirely. And if it does get transmitted as a 1 message, again, this process repeats.
But this other node also has its own prior idea about the state.
So we haven't said anything about how nodes are processing the information yet. And in fact, the agents here won't be Bayesian. So I'll get to that. But right now, all that's happening is mechanically a message that started with the first agent is getting passed along in a potentially noised up way. And so this game of telephone is being played. Yeah, and it may be that the second node also got its own signal, which it is also transmitting. That might also be happening. But we're just talking about so far the message that originated with the very first node.
Oh, so I learn at the end of this chain, this is the message which came from node 5.
Yeah, you might just observe the message, and you in fact here you won't actually know where it came from, but you observe some
But I know in your model that it came from one source. It wasn't sort of corrupted by other messages which got mixed in.
It will get corrupted. And so here I'm just charting out the life cycle of a message that originated with the node on the very left. But in general, things will get corrupted in the way that you're imagining. So after I show you this message passing along the chain, where I'm charting out the life cycle of a single message, I'll show you the actual network and a bunch of different messages originating at different points that are coming in, potentially getting corrupted along the way. So that's going to be full model.
Are you assuming some kind of Markovian property?
Yep. Yeah, that's right. So here things got faithfully transmitted in the first step, and the process is repeating itself. Alternatively, the one message might get corrupted into a zero message, and now there's different probabilities of the zero message mutating back into a one, staying as a zero. And it might be possible that the message actually just gets dropped in this first step of communication. And in that case, then there's nothing else to pass along. Okay, so this process repeats itself. And just as you anticipated, we now have this Markov chain that describes the state that a message is taking on at any step in communication, right? Given with this transition matrix, and in particular, you can see that being dropped is an absorbing state. So once the message is dropped, it remains dropped. Okay, so now let me get to the network. So for each node, we're going to consider the information sources of that node. These are the people who send you things. These are my uncles who send me information on WhatsApp. They have their own sources who they talk to and so on. And so I'm going to assume that my information network, my direct sources, their direct sources, and so on, is a directed tree where the expected number of parents for a node is d. Okay, so I'm going to assume away cycles just because it sort of complicates the analysis without actually changing much the nature of our main results. And the learner you can think of as the root of this tree. And so this is the picture that you should have in mind. So the learner is down here. He has 3 parent nodes. Initially, some nodes received a signal about the state of the world. Okay. Most of them heard 1 signals. One node heard a 0 signal. This then gets passed along to certain nodes in this agent's information network. Here you can see that there was a transmission failure. The message got dropped. The other messages got passed along successfully. They pass along another step. Here there was a message mutation, so the 1 turned into a 0.
So you're assuming each person only sends the message to maximum one other person, or?
Nope. So they could be sending it to other people, but I'm only interested in this learner's information network.
No, but that node on the top, just talk to the guy. In principle, that node could talk to 4 people, and then you have different paths.
Yeah. So here I'm assuming a tree-like structure, but this node might also be communicating to other people who are not in this learner's information network. So it might be telling friends who I have no contact with, and so I don't actually care what happens to what's said to those nodes because that information is never going to come back. But I am assuming a tree-like structure. So there aren't multiple paths for this information to trickle down to those.
So the tree is from the perspective of each learner, but like the union of all these trees, multiple people can be sending multiple messages. Right?
Exactly.
Right.
So, but in general, how do we avoid that it's actually attack and the learner at the bottom has 2 paths? Because if I start to send to various people, you don't even know who is the supposed learner at the end.
Yep.
It's very hard to avoid that for some learners in the network to will get.
Absolutely. So the
So you want an oriented graph such that any node sees only an oriented tree.
that's right. So I'm abstracting away from those concerns.
So the top nodes, for example, will never get to learn anything because they can't. But if I have this tree, so it's.
Well, you can think of it also as an infinite tree. So they might have their own parent nodes, which I'm not picturing.
And I have a question. So originally you had that the one node had a message one and the node other also had a message one. Now the node one passed the message one. So now I have my own information one and the one from my parent. How do I synthesize the two?
So this is a crucial aspect of this model. There are models of communication where you learn from your network, you form some posterior belief, say, and then you send this synthesized message. This is not that. This is, we're passing along physical messages.
So do I pass on all messages?
And we will pass on each of those messages with some probability. And so we're not doing any
one of them
synthesizing.
only.
All of them.
I see.
Yep.
So this learner at the bottom will in general receive many messages, even along the same path.
Exactly.
It will receive several messages.
That's right. Yeah. In fact, yeah, it's probably a good idea to add such an instance to this graph. But yeah, that is totally allowable.
Okay, now I understand.
Yeah. So here, once this process concluded, the learner ended up receiving 3 messages, one of which was a 2 of which are ones. So that's the model of communication. Now I'm going to talk about how we think about the way nodes react to this information. So I'm going to define this quantity m to be 1 minus the sum of these mutation rates. And these are just simple computations which reflect the probability of seeing a 0 versus the probability of seeing a 1 from a message that originated t steps away when the state is 0. And this is the probability of seeing a 1 versus 0 when the state is 1. What you'll notice is, so this t should be in the exponent. What you'll notice is that as t grows large, and so these messages are originating really, really far away from me, both these quantities are going to converge to just the ratio of mutation rates. Right? So whether or not I hear a 1 message or a 0 message from a node that's really far away is really only going to depend on what's the propensity of 1 messages to turn into 0 messages and vice versa. So this is not our model. So this is a model in a companion paper, but let's just think about it for a second. So suppose that the learner actually knows these mutation rates and knows the distances that messages traveled. Right? So messages get tagged with information about the source, and you know how far they traveled before they got to you. If the learner is Bayesian, then he's going to use differences in these frequency ratios to form some posterior. And more signals, meaning broader and deeper information networks, is going to unambiguously mean more learning for the agent. But reality is more complicated. First, this T may be unknown. So messages might not come tagged with information about where they were sourced from. And in this case, we have the sort of corruption that you were talking about, where I don't know if this is a high quality piece of information because it didn't have many chances to get noised up, or whether it's low quality because it's very low fidelity compared to the initial message that was sent out at the source. And moreover, there might also be some uncertainty over these mutation rates mu1 and mu01 that complicate this Bayesian updating problem. Okay? And so what do we show in this companion paper? We show that even with the sort of unrealistic assumption that nodes know exactly what the network looks like, they have really, really tight priors over these mutation rates. They learn in a Bayesian way. It turns out that learning fails as networks grow deep, no matter how broad they are. So even when you endow the learner with all this information, which is going to be unrealistic in almost any real situation you can think of, slight uncertainties over these mutation rates, mu10 and mu01, are going to make it so that as networks grow deep, no matter how broad they are, we won't be able to overcome this slight noise, and we won't be able to learn anything in the limit. And so the nature of that result is then to say that even if there's a preponderance of communication about a particular topic, if people start out with different beliefs, then they're going to get stuck at those beliefs despite all of this communication happening. So they rationally don't update on the basis of the information that they hear. This paper, however, we want to talk about how policymakers can make interventions that actually help the learner. So here in the companion paper, we wanted to prove an impossibility result. Here we want to prove a possibility result. And so we make what we think are more realistic assumptions about the way nodes are learning. We assume that the learner knows little to nothing about the communication process and uses really naive decision rules on the basis of the messages that he or she receives. And we want to ask the question, what can we do to help the learner succeed? And to this end, we consider very simple policymaker objectives that look like this. So policymaker is going to take actions, I'll describe what those actions are, to achieve the following objectives. One could be to maximize the probability that the number of true messages the learner received exceeds the number of false messages.
So when you say naive learning, you mean I believe in one if I see more ones than zero?
Yeah.
So,
another objective could be that I want to ensure that the expected number of true messages that are being sent out on this network exceed the expected number of false messages. Another natural objective is to maximize the expected number of true messages minus the expected number of false messages. And these sort of objectives reflect agents who naively choose actions matching a majority signal, for example. So one way we can sort of microfound this first objective is you can say that agents receive certain noised up versions of messages from their information network and take the action that matches the majority message.
Sorry,
If you're interested in that, sorry.
why did you call that naive? I mean, if you don't know how deep they are or anything, would there be any other information than just going for the majority?
It could be naive in the sense that if you know that people are more likely to mutate messages in one direction versus the other, that messages that are far away are more likely to be of a certain type, and so you might discount that.
You mean so you wouldn't have 50-50, you would have a different threshold, but
You might also start out with different priors over what the states are, and that might also. Right. So this would be maybe sort of one way to think about the reason why we might be interested in that first objective. The agent might take an action A that matches the true state. So maybe take an action 1 if 1 is the true state, and then if 1 is what she believes is the true state, and 0 otherwise, and might get a payoff of 1 if action is equal to the state and 0 otherwise. And a way to sort of think about the second objective is maybe, I hear this communication process run. So the state is realized. I hear some 1s and 0s, but I don't take an action just yet. Tomorrow I hear more 1s and 0s. I still don't take an action. And this process repeats. And after a long time, I end up taking an action 1 and 0. So I hear news about the president every day, but I only vote once every 4 years. And again, if the agent is choosing the majority action, then the policymaker might want to ensure that the expected number of true messages exceeds the expected number of false. Yep. So.
Now you have many possible receivers, right? Because you have one network, many possible receivers. You average these quantities over the nodes in the network. So it's the number of messages, the total number of messages received, summed up for all people.
So here I'm fixing a learner, and I'm looking for the expected number of true versus false messages that this.
So you only optimize for the one learner.
For the one learner, but then later I'm going to think about homogeneous graphs. And so the interpretations will be very similar. Yeah.
Yeah, there's argument that if there is a policy implemented, the probability which commutation of cars remains the same. But if you think that people, let's say, change messages on purpose, you may say that if there is a more stringent policy, people try to engage in malevolent activity.
Absolutely. Yeah. So the way various policy interventions are going to affect the incentives to pass along information are going to be very important. right? And we're abstracting away from all of that, not because those aren't important, but because we can think about 1,000 different reasons why people might send messages. Maybe I send something because I'm trying to inform my friend. Maybe I send something because I don't know if it's true and I just wanted to test it out and put this message out there. Maybe I just thought it was funny, right? So I think empirically it's a question, why do people sort of share the messages that they do, and how should we model incentives? But holding fixed changes, endogenous changes in behavior, we were interested here in sort of studying what are the mechanical effects of these interventions. Yeah.
So like, what is the time horizon when you talk about number of messages? Is just to the limit?
Sorry?
Like when you ask for expected number of true messages and false messages, you're just looking at the limit, the time horizon. Right?
Yeah, so you're just taking an ex ante perspective. So you're you're just you know what these parameters are. Okay, so I'm going to now introduce a little bit of terminology that will crop up later when I show you a couple of propositions. So for mutation rates mu10 and mu01, I'm going to say that a set of nodes in the information network S generates a preponderance of true messages if the expected number of true messages exceeds the expected number of false messages originating from these sources in any state of the world. So once I fixed my set of nodes S in the information network, I'm asking the question, let the communication process run. What is, do I expect a majority of these messages to be true, or do I expect a majority of them to be false?
You're also fixing the learner?
You're fixing the learner, yeah. So you fix the learner, and now you're fixing a set of nodes in the learner's information network. And then you're saying, from the messages that originate from these sources, by the time they trickle down to me, does the expected number of true messages exceed the expected number of false messages? Right? And that's for a given pair of mutation rates, mu10 and mu01. We can similarly define things for a compact set of mutation rates. Right? A policymaker might not know exactly what are the rates with which things are getting mutated, and so they might want to have a more robust objective. And so we say that S generates a robust preponderance of true messages if the expected number of true messages exceeds the expected number of false messages originating from these sources for any state of the world and for any realization of mutation rates. Finally, I'll say that for a compact set of A of mutation rates, the set S dominates S prime if for any pair of mutation rates in A, and in the mutation disfavored state, the expected number of true minus false messages originating from S is weakly greater than from S prime and strictly greater for some pair of mutation rates. That's the state where, so if zeros are more likely to turn into ones than vice versa, then 0 is the mutation disfavored state. Okay, so that's my setup. And now I'm going to think about what are neutral policies that could reduce misinformation. Okay, so here's just a numerical example. So here are the parameters that I have. This probability of transmission is 20% for each step of communication. Zeros mutate into ones 3% of the time, and ones mutate into zeros 10% of the time. And here we had a one message to start, and as it got passed along this chain, after 3 steps of transmission, the probability that that message is true exceeds the probability that it's false. It gets dropped with a large probability. So if we extend this for large T, this is going to be small. Most of the messages that we receive are going to be false when the state of the world is 1, because 1 is the mutation disfavored state. And this switches from being mostly true to mostly false after 7 steps of transmission. So what that suggests is we should be cutting the depth of these networks so that we improve the fidelity of messages that we're receiving and hear more true than false things. If the true state is 0, there's no problem because we're bound to hear a lot of zeros anyways. But if the true state is 1, then the messages that travel too far are more likely to be false. And it turns out that 7.5 is the threshold beyond which things start to be mostly false rather than true. And so this suggests thinking about policies that cap distances that messages travel, and proposition 1 does exactly that. So it says, so there's some expressions up here. You don't need to look at them just yet. It says any given source generates a robust preponderance of true messages. Means messages originating from the source are more likely to be true than false for any pair of mutation rates that you're considering. If and only if the distance from the learner to this node is of no more than t star, where t star is some expression that I have up there. And then we give some interval such that a depth cap is undominated if and only if the depth cap falls in that interval. So caps outside of this interval are not worthwhile because by moving to a cap inside the interval, we can increase the expected number of true minus false messages for any pair of mutation rates. Okay. And this result follows just from the formulas for the frequency ratios that we got. We want to make sure that the probability that we're receiving more true messages than false, the expected number of true messages exceeds the expected number of false messages in any state of the world. And while the exact form of this cap isn't important, what is important is that it's so this is a typo. What is important is that it decreases in the asymmetry between mutation rates. So what's an intuition? If zeros are more likely to turn into ones than vice versa, and these mutation rates are really asymmetric, it suggests that we need to set tighter caps than we would in a world where these mutation rates were more balanced between the two directions. Yeah.
Yeah, so my question is, how do you know whether you're in that state? Like, you live in that kind of world. So if you're a platform, you don't see the content, you can check the truth. So how do you know the transition rates? How can you form
Yeah, so that,
the transition rates?
That's so that's a great question. And the answer is that this is a sort of the reason why we consider this robust preponderance concept. Because you might have a lot of uncertainty about those transition rates, right? You might say zeros are more likely to get exaggerated into ones or vice versa. But regardless of what I conceive as being the possible differences between these mutation rates, let me do something that's robust to all those possible guesses. And so you set a potentially really tight cap if you have a lot of uncertainty about what these mutation rate asymmetries look like. And maybe a stronger cap if you have a stronger sense. But it's going to, again, depend on basically the asymmetry of these mutation rates. That's the object that's really going to drive whether or not the cap is loose or tight. And also fixing the asymmetry, the absolute level of noise in these messages. And capping depth doesn't require knowing any message, right? So we can implement this without actually observing the things that are being sent out. All we're doing is we're making sure that these messages travel shorter distances so that the stuff that we hear has a greater fidelity to its initial source. That's the idea. But the difficulty with a policy like this is it's really hard to implement because we don't really observe life cycles of messages in a lot of contexts. So when one of my uncles sends me something on WhatsApp, I don't know if this was something that he heard from someone directly, a primary source, or if this is something that he learned through the grapevine, right? And because I don't know these things, it's very hard for me as a learner to tell. It's also hard for the platform to tell. The platform in an app like WhatsApp can't even observe the messages that are being sent. Even if you could observe the messages on something like Twitter, you have to ask yourself, is this a new piece of information, or is this a mutated version of something that this agent heard before, right? So following life cycles of messages is very hard. And that leads us to think about breadth caps instead of depth caps. So suppose the communication network is an infinite tree. So nodes have, on average, an in degree and out degree of d. And consider a breadth cap of d prime less than d. That means a node can pass to at most d prime of its neighbors. And if it wants to pass to more, it can't. And so it has to randomly decide which d prime it's going to send a message to. And this is easy to implement as a cap on message forwards. And in fact, platforms like WhatsApp do this. So they say, for example, a given message can be only forwarded to 5 other people. Okay. So what does a breadth cap look like in practice? Well, suppose the probability of passing messages is 1, and you have some regular network that looks like this. Once you impose the breadth cap, a lot of these chains end up disappearing. And so the reason is that the nodes that aren't sending any information to me anymore might have chosen to send to other agents in their network. And so I don't hear the message that came through these nodes. Proposition 2 is an analogous result to proposition 1, but for breadth caps. It says that an infinite depth network generates a robust preponderance of true messages if and only if its degree is less than d bar, where d bar is some function that's given up here. And a depth cap d prime is undominated if and only if d prime falls in a certain interval. Okay. So again, I'm going to tell you about the comparative statics of these things so you don't have to look at those formulas. So first, let's think about why breadth caps work. They work because the ratio of far nodes to near nodes, which the ratio of things that are distance big T away versus little t, is given by this expression here, PD raised to the power of big T minus t. When you impose a cap, this term is going down, and so this gives us one of the 2 punchlines of the paper, which is that caps on communication don't just reduce the total amount of communication that's happening. They actually induce a positive selection effect, whereby they increase the ratio of messages that you hear nearby in the network relative to those that are far away. Okay. Now, next, here's some sort of comparative statics. So the expressions, if you examine them, will show that PD is going to be less than 1 when these mutation rates are not equal. Okay, so that's kind of how you're controlling things. You want to make it so that most of the messages that you hear are nearby. If PD were greater than 1, you would be flooded with messages that appeared from that came down from far away. Moreover, these caps D upper bar and D are decreasing in the max mutation rate and increasing in the minimum mutation rate. So again, we have this result that the more asymmetric these mutation rates are, the tighter you would want to set these caps. And they're also decreasing in this probability P of transmission. So if P is higher, you're more likely to hear stuff that originated really far away. And again, you would want to set the tighter cap. And so this gives us our second punchline, which is that caps help not because there's noise in communication, but because there might be some asymmetry in this noise. If you had 2 things that were very noisy, they're noised up 40% of the time, you would still have that hearing more messages is better than hearing fewer messages, because despite things being noisy, each source is more likely to give you a true message than not. Yeah.
So this is a naive question, but so when you put a depth cap, it's kind of intuitive why you would reduce misinformation, because things are getting corrupted over time, right? Yep. In this case, you get a similar effect just by doing breadth. And I guess I'm just asking, is the intuition behind that kind of just like your friends are more popular than you phenomenon? Because if you take this cap, this ratio, when you have the time going to 1, is it essentially equivalent to that phenomenon?
So is it equivalent to something like the friendship paradox?
Yeah. So similar effect that's giving you this good.
So my intuition from it is that it's basically making it so that once I impose breadth caps, I have to make choices now about which of my friends I'm going to send a certain piece of information to. It means a good chunk of them are going to miss out on it. And that's happening in every step of the way. And so for people who are farther away from me in the network, it's unlikely that through a series of decisions that my message is actually going to reach them. And so it's decreasing the distances that message travel. You're not doing it in the first best way, the way you would with a depth cap, because depth cap, you excise exactly the sources that you don't want, right? Here you're losing also some communication from nodes that appear nearby. On the other hand, it's going to be way more feasible to do something like a breadth cap in a lot of contexts.
But does it also mean that there's just going to be very few messages left in your information?
There are going to be fewer messages for sure. So both policies would cut down on the quantity of communication, right? There would be a sort of trade-off between the number of messages that you get and the quality of the messages that you get. And so here we're only looking at the objective of trying to make sure that the expected number of true minus false messages, for example, is maximized. So the probability that you hear a true message, that a majority of true messages is maximized.
So who decides what's true and what's not true?
No. So that's the idea. The idea is that there is something as a ground truth, right? And you have agents who are taking the action that correspond with the majority of the messages that they hear. And you have a platform that's not telling you that ones are more likely or zeros are more likely and selectively cutting down on them. Instead, the platform is simply pruning the network by reducing its depth if it can, or more realistically reducing its breadth. And doing that makes it so that you're more likely to receive a majority of true messages rather than false ones, because the messages that you get are from sources that are closer to you in the network, and therefore have a greater fidelity to the truth, less chance of getting noised up along the way for various reasons. And so that's the sense in which we say this is sort of a neutral or information agnostic way of improving the quality of information and improving learning without actually taking a stance on what's true or what's false.
So the reason I asked that question is because there may be people close to me who are getting their information from sources that I know are not true.
That's true. So it could be that if you have a bad luck of the draw, then you happen to be in a part of the network where there are maybe more deliberately biased agents.
Yes.
Right? So that could certainly happen ex post. From an ex ante perspective, as long as the messages that people are hearing are more likely to be true than false, the initial signals, from an ex ante perspective, the probability of hearing majority true messages.
Thanks.
Yeah.
So you said WhatsApp caps the number of times you can forward a given message, but it doesn't cap the number of messages that you can send. So in theory, people could, an alternative version of the cap, you can only send one message, the same message, but I can send it to many people. So like I could get many different messages, synthesize them in some way, and then I can send my own version of the messages to many people.
That's right. So synthesizing isn't in this model, but if you did have just one agent sending the same message to many people, that would be that would make it harder to learn in this context. Right? So you do want to. So in practice, when you do set these caps, it doesn't mean that literally now I can't share this kind of information with more than 5 friends. It just means sort of the costs of doing so went up. Right? I send it, and then I have to selectively pick some of my friends and do the same. But that's really, at the end of the day, what we're trying to do. We're trying to increase the cost of sending the same message to a lot of people. So that's I guess.
Well, if it's a good message, we want to diffuse that. If it's a good message, like if you're countering misinformation, we want to massively send that to as many people as possible.
If it's good information, you want to send it to more people. That's right. Here, we're doing a sort of approach where we say, look, I don't know what are the good messages and what are the bad messages. But I know that I can clean up the content that's being sent, at the expense of cutting down the amount of content that's being sent by making sure that messages don't travel too far. And I can achieve that through a breadth cap.
I guess what I was thinking is you could think about a policy where I'm only allowed to send, I can't send the 1 and the 0. It's not allowed. So then I will have to synthesize. And in some sense, your model already, in some sense, the learner is doing it. The learner is synthesizing.
Right.
And so perhaps you could extend the model to allow for the learner, then think of the learner as actually an intermediary who's going to send the message corresponding to the majority.
Yeah.
It seems possible to handle that. I wonder if it's.
Yeah, so we hadn't thought much about that. So one of our ideas in modeling the communication was to say that, in the sort of group models or other social learning tech models, you synthesize information, you form a posterior, and you send that. And we were here trying to communicate the idea that sometimes there's just actual physical mutations in trying to interpret the things that we heard. And we want to sort of capture that kind of noise. I think it's a very reasonable thing to think about a sort of hybrid model that says both that physical messages can get mutated, but also agents selectively pick what it is that they're going to send out on the basis of the stuff that they heard. So I think that would be a very natural.
It might be a reasonable policy. So instead of saying that you can't send contradictory signals.
Yeah. Yeah.
And
but a policy like that would rely on actually observing the message that's being sent out. And that's one of the things that we try to avoid here. So we want to have a policy that actually doesn't even rely on the messages that are being sent. It doesn't require the policymaker to know what's being sent. Okay. So these are just some pictures. So everything that I showed you was in terms of sort of maximizing the expected number of true minus false messages. It's more intractable to work with probability that majority messages are true versus false. But it turns out that these policies, at least in simulations, end up doing very similar things. So here we have a policy of capping the depth of trees for different levels of breadth. So the blue line represents a tree of breadth 5, and the x-axis is different levels of tree depth. And the y-axis is the probability that the majority of signals received from this information network are true. And it seems that here that capping at something like depth 6 or depth 7 is the right thing to do. And notice that that answer doesn't depend on the breadth of the tree, nor should it, right? Because it's actually the distance that individuals' messages travel that matters, and sort of the graph reflects that. The policy that we get from maximizing the expected number of true minus false signals gives a very similar cap here. Notice also that if the tree is very broad, then as the depth gets too large, then a majority of the signals are going to be false, right? Because the tree is really broad and a lot of the signals are coming from far away rather than nearby. Here's just a picture showing a similar graph for capping breadth. Now the lines represent different mutation probabilities. The blue line is the relevant one to compare to for the parameters we've been talking about. And again, it seems that the cap that we get from maximizing expected number of true minus false messages is very close to the cap required to maximize the probability that most signals are correct.
But in order to be able to implement these policies, you do need to know something about the probability, right? So
you need to have some guesses as to how asymmetric these mutation rates get. And you might have a bunch of guesses and you might not be able to pick which of these guesses is true, or you might not even be able to express a prior over these mutation rates. And so the policy that we suggest says, do something that's robust to all of these and set a potentially really conservative cap. Right? So here we get a policy for these parameters. We get a policy that says that we should set a cap of around 4.6. And in WhatsApp, for example, this cap is going to be is 5. Okay. So let's just make some concluding remarks. the model sort of highlights that tagging and tracing messages will enhance learning. Right? So here we're going through all these troubles because we don't know how far messages travel before they reach us, and so we don't know how reliable they are. And so understanding the value of partially tagging messages, could improve things, and studying to what extent it does, I think is an interesting avenue for future work. And I think WhatsApp has introduced some policies that try to do something like this, saying that certain types of messages have been forwarded many times before they reached you, and so on. So sort of giving you some sense of what are messages that traveled far. Here we have that ex ante, all these sort of nodes are the same. One feature that many real world networks exhibit is homophily, and you might have homophily in mutation times. So for example, there might be friends with a group of people who are more likely to say that global warming is not a big deal, or more likely to say global warming is a big deal. And so whenever any information is passed related to this topic, you expect it to be exaggerated more in one way than the other. To some extent, by thinking about a sort of robust preponderance of true messages, we can partially account for this, right? So there might be people exaggerating things in one way or the other, but we're trying to have a policy that's sort of robust to whatever the mutation rate is. But if you wanted to think more carefully about optimizing the way you set these caps, then that's a very different and harder problem. So for example, you might want to loosen caps so that people are more likely to hear messages that their immediate neighbors might not send. And so messages from farther away trickle down that could potentially counteract some of the misinformation that agents are prone to hearing from their immediate neighbors. And so you would have to think about these sorts of trade-offs. Another interesting avenue for research is to think about platform incentives and how they might diverge from regulator incentives. And so I showed a result for breadth caps showing that if you just wanted to ensure a robust preponderance of true messages, you would set a breadth cap of d bar, which is going to be a lot looser than the breadth cap you would set if you want to maximize the expected number of true minus false messages. And you can write down decision problems where a platform might self-impose a cap like d bar if it wants to ensure that people actually visit the platform and aren't blasted with false information, but conditional on that wants to maximize the total amount of engagement. On the other hand, a regulator who's not actually interested in engagement is more interested in whether or not agents are solving their decision problem correctly, might set a cap of d star. And so this suggests that there could be this conflict between policymakers and platforms. And so there's room for thinking about what optimal regulation looks like. And of course, we sort of mentioned that agents might have incentives to communicate, which interact with setting these caps, right? If it happens that people who generate false messages are less likely to do so when there is less chance of their messages going viral, then incentives work in the direction of these caps. But you might also be able to tell stories where people who are actually sending true messages are the ones who are more discouraged from sending out these types of messages. And so incentives are going to play a role when you're trying to consider sort of the cumulative effects of these sorts of policies. And while we study one sort of setting, I think it's important to ask this question in other situations for other kinds of platforms of what are neutral policies that might enhance learning, but don't require the implementer to actually take a stance on what's true and false, and don't require the implementer to police content.
More questions for Suraj.
Yeah, to what extent should I think of this as a model where, I guess, truth is being pegged as a like there's a signal with high probability on the truth, and then there's just some probability that. So in some sense, this is a model about truthful messages being passed. Is that right? And then would it be interested, and would it give the opposite agents to think about someone trying to feed the untruthful message.
Yeah, so I think.
Suraj,
Yeah.
do you mind repeating the question? Or something?
Sure. So the question was that this is a model in which source nodes are more likely to receive exogenous true information than false information. And that drives all of the results. So you want to shorten distances between source nodes and ultimate receivers to improve the fidelity of the initial messages. And improving fidelity is a worthwhile exercise if what's initially being fed into the network is more likely true than false. And certainly if you were in a situation where most of the information that was being fed in is false information, it would suggest that you want to do something very different. But hopefully we're not in such a pessimistic way.
But your model does work if sort of some nodes, some random subset of nodes actually feeds towards Grapevine, as long as they're not in the majority.
Yep. As long as they're not in the majority, things will go through. It could be an interesting question to think about in networks where these sort of malicious agents try to locate themselves. And that might have some implications for how to think about some of these cases, or what the effectiveness of such policies might be. But we see these malicious agents as randomly appearing in different parts of the network in such a way so that the majority of messages that are being passed from an extended perspective are still going to be true.
If there's time.
Sorry, no, please.
Yeah, okay, so yes, following up with that, because this would kind of interact with Malladi. So suppose you have different groups, where some groups are being fed truth, some groups are being fed lies or false. And then shortening the caps, I guess, is going to increase polarization here and would potentially speak to the.
That's a very good point. Yep. So in homophilous networks, shortening caps would create more polarization. It creates these sort of echo chambers, basically, where you're hearing messages mostly of certain types.
So in terms of a policy, I guess you'd want to think about implementing it when it wouldn't harm the, if you
so if polarization is not directly targeting and reducing polarization is not directly an objective of the policymaker, then saying I know some agents are more prone to exaggerating messages in one direction, I know other agents are more prone to exaggerating it in the other, and that there's homophily, so the agents around them have similar behaviors. Then you say, let's just throw these pairs of mutation rates into our set A, and let's set a cap that's sort of robust to A. But if we were thinking about polarization, then we might want to loosen these caps so that messages from far away, which are likely to be different, sort of filter into our local information networks more.
Okay, that's thanks, Suraj again. Thank you.
I would like to make an announcement before you guys disappear. So we were discussing at lunch how we could sort of summarize to the outside world what we're doing at this workshop, because it's very interesting that we're getting together people who study epidemics and people who study information spread, some from an incentive perspective, and then two initiatives we have where we invite everybody to contribute. And actually would like to know how much people do want to contribute. So one is we want to write maybe a paper which says, given that we have passed the epidemic, what did we learn? We don't really want to write policy papers, so we don't want to write, okay, you should do X, Y, Z, but more in the sense, okay, for the next epidemic, maybe we should have models which take into account if people only want to distance for a certain time, when would you distance? Or what kind of models should we have which maybe take into account degree inhomogeneities, or what kind of models we should have to bring in social aspects, things like that. So sort of, okay, after this pandemic, where at the beginning models really failed us much more than they do during the flu season, we don't want to say to people, okay, if you had only distances on day one, everybody would be healthy today. Okay, then we get into chunks of, so that's not the kind of paper we want to write. But we don't want to write a mass paper, right? So we want to write a paper what has the community learned, what would be useful for the scientific community to have or think about before the next epidemic. There are a few of us at lunch who are interested in that, but we want to invite everyone who thinks. So if you have a new mass theorem, hold your breath, we'll talk about that too, but for the moment, that's not the paper we're writing, right? So the second one is more, we are thinking of maybe just having a volume, it could be on the internet or it could be an actual book about summary of talks. Again, I think it's super interesting because, I mean, if you just wrote a book on epidemics, you can write 1 million of them. But there are not that many conferences that bring together these audiences. So this would be essentially to the speakers. If you gave a talk, would you be interested in writing a 1-page abstract or maybe a 10-page abstract, or would be interested in contributing a paper? And we'll look how many of you want to do that. If there are only 3 of you, then we probably just cancel it. If people mainly want to do short abstracts, it's a different thing as people say, okay, we would like to contribute something. So please write to me about both subjects. Write to me, Cecile, Elizabeth, about if you're interested, just let us know. We'll also announce it tomorrow morning.
Yes, and in any case, please don't disappear because Anna is going to give a talk.
Yes.
In 30 minutes.
Disappear.
Yeah, thank you.